So when we're working with circles in trigonometry, there's a great circle that gives us a lot of information about all of the angles from 0 to 2 pi radian and from 0 degrees to 360 degrees. And that's the unit circle. And the way we would create the unit circle is by letting the radius be 1. And when we do that, all of the r's in our previous trig definitions become 1, so our trig definitions become simplified. So sine of theta, which was previously computed as y over r, is now y over 1, or simply the y value on the unit circle of the point on the edge of the circle. And cosine, which was computed as x over r, is now x over 1 on the unit circle and just has the value of the x point on the edge of the unit circle. And tangent is y over x, the same as before. And so here you can see cosecant, secant, and cotangent are those reciprocal functions as well. So you should know the unit circle by now, but if not, I'm going to show you some of the patterns on the unit circle and we'll practice filling one out ourselves, because if you can learn the first quadrant, then all the symmetric properties of the circle can give you a really quick way of computing the rest of the circle. So in quadrant 1 here, you'll notice that I have the coordinate 1, 0, because I'm letting the radius be 1 on the x-axis, and the coordinate 0, 1 on the y-axis, corresponding to 0 degrees and 90 degrees, or 0 radians and pi over 2 radians. And so in this first quadrant are 3 of our reference triangles. First, if I let this angle here be 30 degrees, then I have my 30-degree reference angle, and 30 degrees corresponds also to pi over 6 in radians. So now I know my x-coordinate is my cosine, so cosine of 30 is square root of 3 over 2, and sine of 30 is 1/2. And so if you kind of think about the x value here, the x value is square root of 3 over 2, and it's further along, it's closer to 1. So square root of 3 over 2 is larger than 1/2, and so we see that we have the larger x value in this guy, and the shorter y value, y is only 1/2 for 30 degrees. Then if we continue up to this green triangle, then we have 45 degrees, which corresponds to pi over 4 radians, and that coordinate on the edge of the circle is located at square root of 2 over 2, square root of 2 over 2. So these come from our reference triangle, but that tells me that both cosine and sine of 45 have the value square root of 2 over 2. And then if we travel a little bit further, we get to 60 degrees, or pi over 3. And again, here we have a smaller x value, 1/2, and a larger y value, square root of 3 over 2. But this location here gives us both the cosine and sine of 60 degrees. What we didn't discuss before in our reference triangles was 90. And so the quadrantal angle here, pi over 2 or 90, can still be computed using the definitions above. So we know that the cosine of 90 is 0, the sine of 90 is 1, and so the tangent this time would be undefined because we can't do 1 divided by 0. So what I want to review with you are some of the symmetric properties and the patterns, because if you can create on your own the first quadrant of the unit circle, then you will know the trig functions of all of these reference angles around the entire unit circle, keeping in mind that all students take calculus and keeping in mind these 3 reference triangles here. So in your packet you had a blank unit circle. So what I want to do is show you how I label it with the patterns that I found and how you can use the symmetric properties to figure out the sine and cosine of all of the angles on the unit circle. So grab your blank unit circle, and it looks like this. And we're going to start in degrees because sometimes that's easier to kind of count. So we have a completely blank unit circle, and the first pattern we need to recognize is that if we ignore these perfect middle lines here and just think about the first, starting at 0, our first point, skip our second point and our third point, we can count by 30 degrees and start labeling all of those angles. So for example, I'd be starting here at 0 degrees, and then if I count by 30, I'll get 30 degrees, 60 degrees, 90 degrees, 120 degrees, 150 degrees, 180 degrees, 210 degrees, 240 degrees, 270 degrees, 300, and 330. One full rotation gets me back to 360. So that's one way to count in degrees. But then I need to go back and fill in the angles that cut the quadrants in half. And to do that, I need to count by 45s. So 0 degrees, 45 degrees, 90 degrees, 135 degrees, 180 degrees, 200, why can't I count? 225 degrees, thank you, myself, 270 degrees, and then 270 plus 45 is 315 degrees. So degrees is sometimes the easier pattern to find, but we can use that same counting mechanism to label the radians as well. And so if we look at the smallest and follow the 30, 60, 90, 30 degree pattern, we can do the same for radians. And so what I suggest is keeping things not in lowest terms to start until you get the pattern, and then reducing the fractions as you go if we count by pi's over 6. So let me show you how to do that. 0 radians, pi over 6 radians, 2 pi over 6 radians, 3 pi over 6 radians, 4 pi over 6 radians, 5 pi over 6 radians, 6 pi over 6 radians, 7 pi over 6, 8 pi over 6, 9 pi over 6, 10 pi over 6, 11 pi over 6, and 12 pi over 6. Now, of course, these aren't in lowest terms, so you have to go back and see if you can reduce those to have the radian measure in lowest terms. Pi over 6 is, but 2 pi over 6 reduces to pi over 3. 3 pi over 6 reduces to pi over 2. 4 pi over 6 reduces to 2 pi over 3. 5 pi over 6 is already reduced. 6 pi over 6 reduces to pi. 7 pi over 6 is already reduced. 8 pi over 6 reduces to 4 pi over 3. 9 pi over 6 reduces to 3 pi over 2. 10 pi over 6 reduces to 5 pi over 3. 11 pi over 6 is already reduced. And 12 pi over 6 reduces to 2 pi. So you can count, then you can label. So we have to do that same pattern with pi over 4. So 0 radians, 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4, and 7 pi over 4. The pi's over 4 are also already reduced. So there's how you can create a unit circle and measure the angles. So next step, we actually have to fill in the coordinates, or the location of the points on the edge of the circle. So let's start with the easy ones, the quadrantal angles, the ones that are on the axis. So over here, we're at the coordinate 1, 0, x is 1, y is 0. So that's the coordinate for 0 degrees, 0 radians, 360 degrees, and 2 pi radians. Now if we go up to 90, we're 0 on the x-axis, but 1 on the y, because this is the unit circle with radius 1. So we know sine and cosine now for the 90 degree pi over 2 angle. We come around to pi, or 180 degrees. We're at negative 1, 0. And finally, down at 3 pi over 2, we're at 0, negative 1. So we can label those quadrantal angles first, and then next up we just need to label the first quadrant and then use the symmetric properties and the fact that all students take calculus, and we can fill in quadrants 2, 3, and 4. So here in quadrant 1, let's first talk about the x values. So starting at 90, x is 0, and as we move along the unit circle, x increases to 1. So x is going from smaller to larger. So there's a pattern here. If you can do square root of 1, square root of 2, square root of 3, notice that they're getting bigger. 1, 2, 3. And then using our reference triangles, we know that the cosine of 60 degrees is 1/2 if you reduce square root of 1. and square root of 2 over 2 is cosine of 45. Square root of 3 over 2 is cosine of 30. So now look at the y values. The y values starting at 1 and decreasing to 0. So the y values decrease. So if you can remember going smaller, square root of 3, square root of 2, square root of 1, then you can also remember the y values. They're all over 2 because of our reference triangle. So there you have it. Now you have the sine and cosine of pi over 6, pi over 4, and pi over 3, and you know that all students take calculus, so we can use some symmetric properties and fill in the rest. So I'll do quadrant 2, and then you can go ahead and try quadrant 3 and 4 on your own and confirm them with the filled-in unit circle that I already gave you. So let's just talk about symmetry over here in quadrant 2. So take a look at what's going on at 2 pi over 3. Notice they have the same y value. They're on the same location on the y-axis, so they both have a sine of square root of 3 over 2. But notice the symmetric property in the x's. Here in quadrant 1, x is positive, but in quadrant 2, x is negative. So 2 pi over 3 has a cosine of negative 1/2. Do the same with 3 pi over 4. Notice they have the same y value, the exact same y value, so that's square root of 2 over 2. But x is reflected, so in quadrant 1, x is positive, but in quadrant 2, x is negative. So that's negative square root of 2 over 2. Lastly, look at 5 pi over 6. 5 pi over 6 has the same y value, the same location on the y-axis as pi over 6, so that reduces to 1/2 or square root of 1 over 2. But again, x is positive in the first quadrant, but negative in the second quadrant, and so we have negative square root of 3 over 2. You can do that same thing using symmetric properties from quadrant 2 to quadrant 3 and from quadrant 1 to quadrant 4 and fill in the rest of your unit circle. So before you take a test, you should practice drawing this unit circle and just keep trying to learn the patterns in quadrant 1, because then you can be confident that you can fill out the rest. Because decimal approximations won't be acceptable in this class. You're going to need these exact values, and so the unit circle is a great way for you to get that, since your calculator always gives decimal approximations. So practice making your unit circle.